if you apply exactly the weak law of large number to the empirical risk and the true risk, you get the following inequality. Because the empirical risk is, as we've argued before, a sum of ID random variable normalized by n, it is exactly the setup we have in the weak law of large number. And we already established that the true risk, or that hypothesis Hj, which is fixed here, is the mean of that random variable. Everything is ID, that's by construction of the model. And therefore, for any epsilon, the probability that the empirical risk exceeds the true risk in absolute value by more than epsilon is bounded by the variance of the random variables that matter divided by n epsilon squared. What are the random variables that matter? They are the xi's in 1 over n sum from I equal 1 to of the xi, which in our case here is an indicator function. It's an indicator function hg of xi not equal to yi. And here I've replaced I by 1 because by ID-ness, I can choose any of these random variables to compute the variance. The key point here is that because the indicator function is between 0 and 1, if you take the variance of a variable that's between 0 and 1, you can always upper bound it by 1. And as a result, a loose bound on that probability on the left is simply 1 over n epsilons. So what is it telling us? It's telling us that as n gets large, for a given hypothesis Hj, it's actually quite likely that my empirical risk gives me a good estimate of the true risk of that hypothesis. So that's good news. It's telling us that given enough data, represented by n, the number of feature vectors in your data set, you can generalize. Because if you fix a model, you evaluate it on a huge data set, the risk that you're evaluating is actually going to be very close to the average loss function. So you can generalize. Now the question, of course, is how much data you need to generalize. So there, to talk about generalization, you need to introduce another parameter. You have to say, well, this is a probabilistic statement that I'm trying to make. So let me ask that the probability that the empirical risk be away from the true risk in absolute value by more than epsilon be less than delta. And you can see from the bound that we just established that it's telling you that the number of data points that you need to meet that requirement of that probability being less than delta is 1 over delta epsilon squared. And it's actually a fairly natural result to read. I don't know if it's natural to prove, but it's very natural to read. It's telling you that if you want epsilon to be small, the number of data points that you need is going to blow up. If you need delta to be small, the number of data points that you need is going to blow up. Now, are we done? Not quite, unfortunately. What we've proved is not quite enough, because what we care about is not just saying that we can generalize a given model Hj. What we care about is proving that we can generalize the best model H star that we find by empirical risk minimization. Said differently, what you care about in your machine learning problem is not you saying, let me try a completely random model, evaluate its performance, and think that you'll be done. There's some hard work to do to actually find a good model that tries to best explain that unknown function f that you're after. And the approach that we've chosen is to choose H star to be the best model in your class that minimizes the empirical risk. That's empirical risk minimization. Write it explicitly here. So this is called empirical risk minimization, or ERM. And I'm claiming that understanding how to bound the probability that the empirical risk of H star differs from the true risk of H star by more than epsilon is actually slightly more complicated. We're going to go through it together, but I want you to understand intuitively why it's complicated. To talk about H star, you have to be able to claim that H star is indeed the hypothesis that gives you the minimum risk. But to claim that it's the minimum risk, you have to be able to say that you've evaluated the risk of all the other hypotheses Hj. And what's happening here is something a little bit subtle, so bear with me for a second. If you are in a situation when the size of the hypothesis set M is very large, what we have proved is we have proved that for every one of these Hj in the hypothesis set, the bound that we just established holds. It says that as n gets large, the probability that the empirical risk will be away from the true risk is going to be small. But unfortunately, because you have many hypotheses in your set, it is possible that that probability here, the statement is probabilistic, the event is actually violated for some of the hypotheses in the set. And that's what I'm trying to write here. When M is large, we should expect that even though for many models, it will be true that they generalize, some of them will not generalize well at all. And that's just a consequence of the fact that the statements that we're making are probabilistic. When you look at a single model, of course, as n gets large, it has a high probability of generalizing. But when you look at all the models in your set H, that probability that all of them generalize at once is going to be much, much worse. Because the statement that we established is only for a single model, not for all models at the same time. And as a result, we have to be a little bit careful when we try to analyze the generalization of H star, because H star is defined knowing all the other models Hj, because it's defined as the one that minimizes the empirical risk of all the other models. So we have to be a little bit careful. And unfortunately, analyzing the probability of the empirical risk of H star is very complicated. And it's very, very complicated because if you think about it, the minimization requires you to understand the interplay between all the different models. And the only bound that we have access to easily is a bound that says that the probability that the empirical risk of H star exceeds the true risk of H star in absolute value by more than epsilon is upper bounded by the probability that there exists a model for which the empirical risk exceeds the true risk of that model in absolute value by more than epsilon. This is not a very good bound because it kind of totally hides the fact that there could be some of the models that are very similar, some of them that are very different. Everything here is hidden, but it's very hard to analyze the fine details of the event on the left-hand side, and therefore we resort to a fairly general upper bound. Okay? So intuitively, what is that upper bound true? In my opinion, it's slightly easier to understand the contraposition of that statement here. And what I mean by contraposition is the following. What I find easier to understand is the following. Let's imagine that we look at the probability that the empirical risk of H star is less than epsilon away from the true risk of H star. So this would be an event that says the probability that R hat n of H star minus R of H star less than epsilon. So for that event to be true, it means that the best model in your hypothesis set satisfies that quantity. So for that to happen, you just need one model to work, right? You don't need all the models to satisfy that constraint, just one. And therefore, that probability has to be greater than the probability that for all models Hj, the same statement would be true. R hat n of Hj minus R of Hj less than epsilon. All right, so again, the rationale here is that requiring the minimum to the best model, H star, that minimizes the empirical risk to generalize well is much weaker than requiring all the models to generalize well, and therefore the probability that the minimum generalizes well is higher than the probability that all models generalize. Now, if you realize that the equation I wrote before is just 1 minus what I wrote below, you get the statement. Okay, and the contraposition that for all model you generalize is that there exists a model that doesn't generalize. But I think that second form, which I highlight here with a star, makes very clear that it is not a very good bound, because we're completely ignoring the fine possible dependencies of the different models in the class. And unfortunately, without me telling you more about the models, you can't do more about it. So it's a bad bound, but that's the best that we can really hope for at that stage. All right. So what? I mean, we would still very much like to get a bound on the left-hand side because that's the probabilistic statement about our ability to generalize the hypothesis H star that we find by empirical risk minimization. And unfortunately for us, the only tool at our disposal is something called the union bound, which is a terrible bound that will lead to the following. Will lead to us upper bounding the probability that the empirical risk of H star exceeds the true risk of H star in absolute value by more than epsilon by m, the size of the hypothesis, by n epsilon squared. So let me prove that statement. It just requires one line. So that statement is obtained from the previous one as follows. If you look at the probability that there exists a j from, j takes values from 1 to capital M, the number of models that we have in our hypothesis class. So there exists a j such that the empirical risk r hat n of hj exceeds its true risk r of hj by more than epsilon. It's also very complicated to analyze. I don't know how these models are distinct from each other, but what I can always do is I can always say, well, it's always less than the probability, the sum, from j equal 1 to n, that the probability of every model doesn't generalize. All right? So that's always true. It's a very bad bound, but it's always true. And now, what I have done before, in my previous analysis, when I was analyzing a specific model, I came up with a bound on this. And my bound was to bound that by 1 over n epsilon squared. So now it's a constant bound, doesn't depend on j anymore. And so you get exactly the upper bound that you're after, which is m over n epsilon squared. So let's put that together and interpret what's going on. What we have done is, through the use of essentially the weak law of large number, we've been able to come up with probabilistic bound on the event that the empirical risk differs from the true risk by too much. And if that happens, we know it means that our model doesn't generalize well. And what I've argued is that when it comes to analyzing the ability to generalize based on the H star, the solution of empirical risk minimization, unfortunately, the bound is pretty bad. We take a penalty that depends here on m, the size of the hypothesis class. And the reason that m shows up intuitively is because to ensure that H star generalizes well, you have to make sure that most models actually generalize well. And the only way you can really analyze that precisely at that stage is just to use a very loose bound where we say, well, H star will for sure only generalize well when all models generalize well. And therefore you get that bound. Now, if you now ask for that upper bound to be equal to some delta, you want to say the probability to not generalize to be 0.1, you take delta to be 0.1, you can solve for n again. And the answer that we get is that to make sure that the H star that we obtain through empirical risk minimization actually generalizes, we need n to be on the order of capital M, the size of your hypothesis class, divided by delta epsilon squared. So again, we get the behavior as a function of delta and epsilon squared that we had observed before, but we're getting insight now into the effect of the model class into our ability to generalize. You see that the number of samples that you need has to be scaling with the size of the class. So if you have a very complex class of models, imagine you're using a deep neural net, and I'm pushing it because the class of models that you can use with a deep neural net is actually infinite. But you see, this would predict an insane number of samples that's totally unfeasible, and that would suggest that we cannot learn very well. And there's a question from David. So M is the size of our set of models. Absolutely. I think I defined it right here. So here M is defined as the cardinality of the hypothesis set, which we assume is finite. So that result is actually quite disappointing in a way, because it really tells us we need an insane number of samples to get a good generalization done. So is that the end of the story? In a way, the fact that we need quite a few samples to actually learn a model well is not surprising to us. What's a bit disappointing here is the fact that it's predicting a lot of samples. And in particular, I would like to be able to have fairly complex models. Let's say I have a complicated function to infer through machine learning. I want to have a model class that allows for complicated functions. But if the size of the class of models is too large, it's telling me I need an insane number of samples. So it turns out that even though what we've done here does capture everything that matters about bounding this probability of not generalizing, we were suffering from the fact that the weak law of large number, which is really Chebyshev's inequality here, is a pretty weak result. The fact that we could establish it in 30 minutes is a sign that it's not that complicated and not that powerful. But it turns out, thankfully, that we can use not so basic concentration inequalities to improve our result at almost no cost, reproducing the same reasoning without all the penalties of the weakness of Chebyshev's inequality.